The method of Lagrange multipliers is, at least in my view, one of the great magic acts of multivariable calculus. It's a simple idea that proves itself to be extremely powerful. The underlying logic can feel a little confusing at first, and the actual computational process can sometimes be complicated, but it's such a clever and insightful way to solve the problem. What is the problem? In the previous section, we were trying to find the extreme values in a two-dimensional region. The second step was to find the critical points along the boundary of the region. For a simple region, like a rectangle or a circle, it's not hard to set up the parameterization. But if the constraint were any more complicated, it would basically be impossible to parameterize it. The method of Lagrange multipliers does this step without parameterization at all. We're going to be working with two functions. The first function is f, which is the function that we're trying to find the minimum and maximum values for. The second function is g, which is the constraint equation. We are going to assume that we can write the constraint as g of xy equals c, where c is any constant. Some books write that as g of xy is equal to 0, which makes no difference at all to the method. Let's imagine a graph of the level curves of f. Remember that these are the curves that represent a constant value of the function. To make this picture concrete, we're going to imagine this representing a mountain with the peak in the middle of the circles. Now let's think about the constraint equation. The constraint equation creates a path along the function. Every time our path cuts across a level curve of f, we must be going either up or down. For example, at this point we're climbing up the mountain, and at this point we're descending down. Somewhere in between going up and going down, there must be a point where we level out. And that point happens where our path is tangent to the level curve. It is at that point where we are no longer cutting across level curves, but instead traveling along one of them. And that's our first observation. The critical points along the constraint happen where the constraint is tangent to the level curves. Recall that the gradient of f is a vector that points perpendicular to the level curves of f. Let's focus on the gradient at the point of tangency. That vector is going to be perpendicular to the level curve, which means that it's also perpendicular to the constraint curve. We want to find another representation of the direction that's perpendicular to the constraint curve at that point. And the trick is that the equation g of xy is equal to c is the equation of level curve of the function g. And so the gradient of g gives us a direction perpendicular to the constraint curve at the point of tangency as well. And that gives us our second observation. The gradients of the two functions must be parallel to each other. We know that two vectors are parallel to each other if they are scalar multiples of each other. And so the gradient of f must be a scalar multiple of the gradient of g. And that gives us the core relationship for Lagrange multipliers. The upshot of all of this is that this very simple formula is the way that we can solve for the extreme values of the function along the constraint. To find the extreme values, solve the system of equations given by setting the gradient of f equal to a multiple of the gradient of g. This symbol is called lambda, and it's the Greek letter L. Solving this will locate points along the constraint where the directional derivative is equal to 0, which is basically the same idea as the first derivative test of single variable calculus. Now I realize that not everyone will appreciate just how cleanly these ideas come together into this formula, but I would encourage you to think through it a couple times for yourself and really try to make the connections. It brings together a number of ideas from across the last couple chapters into a nice package. But at the end of the day, for a course at this level, you just need to show that you have the ability to solve the equation. The process itself is simple. You calculate the gradients, set the components equal to each other, and solve for the variables. A good trick for this is to not divide by any variables, because that could lead to division by 0. Instead, you want to multiply and factor using substitution or elimination. I don't quite like how the book does this example, so we're going to briefly overview the steps that I would use to solve the problem. You can pause the video to read the steps line by line, but this is something you should take as an outline and work through the algebra yourself. The function f that we're trying to optimize is x squared y, and the constraint is the equation 4x plus y equals 108. Notice that the function g is the left side of the constraint equation. When we plug this into the Lagrange multiplier equation and set the components equal to each other, we get 2xy equals 4 lambda and x squared equals lambda. Don't forget that we also have the constraint equation 4x plus y equals 108. There are 3 equations and 3 variables, and so we can begin to solve this. If we directly substitute for lambda in the first equation using the second equation, we get 2xy is equal to 4x squared. Moving everything to one side and using the fact that x is positive, we see that y is equal to 2x. We can then plug this into the constraint equation, which gives us x equals 18 and y equals 36. This is the only critical point under the conditions that x and y are positive. If we took away that restriction, then x equals 0 becomes another critical point. But for this problem, having found the critical point, we simply plug it into f to get the extreme value. And that's the basic flow for how we solve these problems. In some cases, you may have multiple critical points, in which case you just plug them all in and identify the largest and smallest values. Notice that the final conclusion was written as a complete sentence. I really want to encourage you to get into that habit. The formula for Lagrange multipliers works for any number of dimensions. Activity 10.8.3 gives you an opportunity to do such a problem. You are strongly encouraged to work through that one, because experience is really the best way to learn this technique.